Now we'll study the selection rule for rotational spectra, which is delta J is equals to plus minus 1. J is the quantum number for rotational spectra. Now if J is equals to 0, it is ground state. J is equals to 1, first excited state. J is equals to 2, second excited state, and so on. So the possible possibilities are for the transition from J is equals to 0 to 1, or from J is equals to 1 to 0, and transition from J is equals to 1 to J is equals to 2, or from J is equals to 2 to J is equals to 1. Just these are the possible transitions, and from J is equals to 0 or to 2 it is not possible because the delta J can be plus minus 1 only. Now there is a question: identify the intense transition, and the given options are these. So in the first transition, J is equals to 7 to J is equals to 9, the delta J is 2, so it is not possible. In this, delta J is minus 1, but J is equals to minus 1 is not possible. The lowest J is 0. So this is also not possible, and J is equals to 7 to J is equals to 5, delta J will be 2. So it is also not possible. So the correct option is none of these. Now if we solve for the delta E value, then it will be EJ dash minus EJ, where J dash is the where the transition is from J to J dash. So the J dash we are assuming it to be J plus 1, so because we are taking this at higher, so J plus 1. Then putting the we know that E is equals to energy is equals to J into J plus 1 B. So now here it is J dash, here it is J. Putting J dash is equals to J plus 1, we get this. And then on solving this by taking common J plus 1b, we get 2 whole bracket J plus 1b, where J is the quantum number of lower state. So delta E is equals to 2 into J plus 1 into B. Now delta E value for these following transitions are: for J is equals to 0 from the for the transition 0 to 1, we have 2b. For the transition of J is equals to 1 to 2, it is 4b delta E value. Then for the transition 2 to 3, it is 6b, then it is 8b, then it is 10b, so on. So the difference between any transition is 2b. Any consecutive transitions, it is 2b. So rotational spectra is a series of line, and each line is separated by a constant, that is 2b. These are series of lines, and each line is separated by 2b. Now we'll discuss two questions. In a diatomic molecule, separation between first and fourth line is 100 centimeter inverse. Calculate the energy of fifth rotational state. So what is given is the separation between first and fourth line. So if we assume this as first line, that is 2b, and fourth line, this is first line, second line, third line, fourth line. Fourth line, it is 8b. So separation between both is means 8b minus 2b, which will be equals to 6b. So this is, for example, this is first line, second line, third line, fourth line. So separation, total separation is 2b plus 2b plus 2b, that is 6b. So it is given as 100 centimeter inverse. So 6b is equals to 100 centimeter inverse. So b, what will it come? 100 upon 6. Now it is asking the calculate the energy of fifth rotational line. Fifth rotational line, that means we don't have to use the formula delta E, we use the formula of E. So E formula is J into J plus 1b. So J, we have to find the energy of fifth rotational line. That means fifth rotational line is this first, second, third, fourth, fifth rotational line. In fifth rotational line, the transition is from 4 to 5. So we will write the lower J value. So 4 into 4 plus 1 b. So when we will solve it, putting the b value from here, we will get as 1000 upon 3. Similarly, another question, energy of second excitation level is 300 centimeter inverse. Calculate the position of fifth rotational line. So for ground state, J is equals to 0. For first excited state, J is equals to 1. For second excited state, J is equals to 2. So the energy of second excited level, that is J is equals to 2, is 300 centimeter inverse. So we will use the formula of E is equals to J into J plus 1B. So J is equals to 2 for second excitation level, so it will be 2 into 2 plus 1b, that will be 6b, and its value is given as 3 centimeter inverse. So 6b is equals to 300 centimeter inverse. So 6b is equals to 300 centimeter inverse. So b will be 300 upon 6, that is 50 centimeter inverse. Now we have to calculate the position of fifth rotation line. Position, that means we have to calculate the delta E value, and delta E value can be calculated by two methods of fifth rotational line. So first rotational, second rotational, third rotational line, fourth, fifth rotational line. For fifth rotational line, the transition is between 4, J is equals to 4 to J is equals to 5, and we know that the delta E values are this for each line: 2b, 4b, 6b, 8b and 10b. So for fifth rotational line, we can directly calculate as 10b if you remember it. So b value is 50, so it will come, the delta E value will be 500 centimeter inverse, or you can use the formula delta E is equals to 2j plus 1b, where j is the quantum number of lower quantum number of lower state, that is 4. J is equals to 4 for fifth rotational line, so we can put it as 4 plus 1b, which will also come as 10b. So because here these values are calculated from this formula only, 2j plus 1, so 10b, so 10 into 50, b we have calculated here, so 10 into 50 centimeter inverse, which will be 500 centimeter inverse.